In the next four videos, starting from this one, we'll be talking about random walks, which is like the primary thing we can think about when we talk about stochastic processes. So, simple random walk. By definition, a simple random walk is given as Sn equals x1 plus x2 plus all of that up to xn, where each xi is independent. That is, x2 is independent of x1, x3 is independent of x2, and so on and so forth. And x1 can only, xi can belongs to just two collections. It can take two forms. X1 can either be plus 1 or minus 1. And the probability that xi is plus 1, we can take that to be p. And probability that xi is minus 1, we can take that to be 1 minus p, such that when we add up the two probabilities, everything goes to 1. So we have a special case of random walk when p is 0.5. And when p is 0.5, it means that probability that xi plus 1, xi equals plus 1 is 0.5. And probability that xi equals minus 1 is 1 minus 0.5, which is also 0.5. And we call that a symmetric random walk. So for a symmetric random walk, there's equal probability of xi being plus 1 or minus 1. So the intuition is that when you start at a position 0, at each step you move right, that is plus 1 with probability p. Then you can also move left minus 1 with probability 1 minus p. So this models cases like gambling outcomes, stock price movements in the simplified form, or even random motion in physics, right? So imagine something like this. You start at a particular location. So you have this now. So you can go to the right, that's plus 1, with a probability of with a probability 0.5, or you can go left, with a probability 0 and with another probability 0.5. So, but let's assume that it goes right the first time, and then after that it goes right again, and then next one, um, I'm trying to see what that should really look like. Move right plus 1 with probability p, and move left with probability 1 minus p, like that. So, I mean, you just keep moving like that to right or left, depending on the current location. So, um, we have those examples in gambling, stock price, and of course, random motion in physics. Then we talk about the expected value. So for the expected value of the random walk is given as expected value of S sub n. You know, we already said S sub n is the summation of x1 plus x2 up to the last point. Okay, so the expectation of the random walk is equal to n into 2p minus 1. So, and then the special case, the special case, well, actually, um, why do we have this, right? Because we already know that if we have two possibilities, let me try to imagine what we can have here, right? So the expectation of Sn, so especially when we have just those two states now. So we have, say, probability P of going to minus 1 plus probability 1 minus P of going to plus 1, I believe. So we have okay, then we now have the number of steps taken and things like that. But let me just do this one like for one step. So we have minus P, all right, plus 1 minus P. So that's like 1 minus 2P. So that's just for one step like that. So this is 1 minus 2p. And then when we talk about the number of steps taken, okay, this is 2p minus 1 now. Um, okay, let me see. I think, did I get this right? So probability plus 1 is p is plus 1. Yes, I think that's where the issue is. So the probability, so p is plus 1 and 1 minus p is minus 1. So that changes it accordingly. So we have p minus 1 minus p like this. So that is p minus 1 plus p. So we have 2p minus 1 for just one situation. But if so, and since we're talking about n steps now, so all of this will be multiplied by the number of steps taken. Okay, number of steps taken. So because this is Sn already, so then that will be n into 2p minus 1 as we have it there. So n is 2p into minus 1 based on the probabilities and the points. So special case when p is 0.54. So when p is 0.5, of course, um, we have that symmetric case. So at p equals 0.5, we have that the expectation, so that's a special S for symmetric random walk. So at p equals 0.5, we have that the expected value of Sn, right, is equal to n into 2 into times 0.5 minus 1, and that is n into 1 minus 1, which is n times 0, and that is equal to 0. So a symmetric for a symmetric random walk, we have that the expected value of Sn is equal to 0. Okay, so if there's equal probability of going left and right, the expected value is 0. So then we talk about variance now. So the variance is the variance Sn, that is 4np into 1 minus p. Of course, if you can get the moments, we can always arrive at this later on. So the variance of Sn is 4np into 1 minus p, and for p equals 0.5, the variance of Sn is n. So for that special case of symmetricity, expected value is 0 and variance is n. So let's take an example. We have symmetric random walk now. A particle takes 5 steps with p equals 0.5. So expected position, of course, will just be 0 like that. And variance will be 5 easily. Okay. And then for example 2, when we have a biased random walk, so let p be 0.7 and there are 10 steps taken. So the expected value of S10 will be 10 into 2 times 0.7, all right, minus 1. That will be okay, this is 2 times 0.7, right? Minus n. Okay, this is 2p minus 1, yeah? That's 2 times probability minus 1. That is 1.4 minus 1. That's 10 into 0.4, which is 4. So the expected value is 4. In that case, of course, if the variance would have to now be computed based on 4np into 1 minus p, like that. So, okay, I think I can go on with that, right? 4np into 1 minus p. So we have that p, so for p equals 0.7 and n is 10, we have that the expected value of S10 is will have to be n into 2p minus 1, right? Okay, this is still for Sn. So for expected value of S10 now, we have n, that's 10 into 2 times 0.7 minus 1, like that. So that is 10 into 1.4 minus 1. So that is 10 into 0.4, and that is simply 4, like that. And then we go on to the variance of S10 Sn, variance of Sn is 4np into p minus 1, if I got that right. So variance of Sn is 4np into 1 minus p. Yeah, 4np into 1 minus p. 4np into 1 minus p, yeah. So, so we have 4np into 1 minus p. So again, n is 10 and p is 0.7. So the variance of S10 would be 4 times n, which is 10, and p 0.7 into 1 minus 0.7 again. So that's 4 times 7, that's 28 multiplied by 0.3. Yeah, 40. So yeah, that's 4 times 7, 28. So 28 times 3 over 10. That's 3 times 8 is 24. We carry 2. 3 times 2 is 6 plus 2, that's 8. That's 8.4. That's the variance. The variance is 8.4 in that case. So we go on like that. So for a biased random walk. Then we have another case. we what about with probability of returning to the origin? So what's the probability of returning back to zero? So imagine that we have you want to find the probability that S4 is equal to zero. That is the fourth step gets back to zero for a symmetric random walk. So to return to zero, we need two steps right and two steps left. So to get back to zero, right? Two steps right and two steps left. So that's uh like what I was trying to do originally. So probability that when you start, take four steps and you get back to zero. So it means you take step one, step two, right, and then you now come back step three, step four, three, four, and you're back at zero. So that's very important. So in this case now, so the number of ways that this can happen is you have 4 combination 2. So 4 combination 2 is equal to 6. So each path probability will now be 1 over 2 raised to power 4. And that is 1 over 16. So the total probability now will be probability S4 equals 0 now will be 6. Okay, the number of possible ways, right? That will be 6 times the probability that that happens, and that will be 3 divided by 8. And we can simulate that using using the code. So random walk for one path. This is an example of that. So you just declare, okay, like this simple random walk now is just this single random walk is just a it's not just a generalization on how to demonstrate that random walk. So it doesn't have anything to do with what we have just done directly. Then, of course, since it's random, right? The more you run it, the more it changes. So you can see it's always changing because it's random. Okay, it keeps changing like that. Okay, so we can also have multiple random walks as you see here. So you have multiple random walks. So this is what that looks like. But if you keep running, it keeps changing. So you have multiple random walks, keeps changing. So then we can also talk about the mean and variance simulation. So for that kind of random walk, so you compute this. So here n is 100, and then number of simulations is 10,000. So we have all this now. So the values keep changing as we keep simulating like that. So we have the estimated mean and the estimated variance. So some possible extensions we can have to this whole thing. We can look at a two-dimensional random walk that is movement in 4 directions. And then we can have continuous limit leads. Continuous limit leads to Brownian motion. And then applications can be found in finance, physics, and biology. We're going to see more of this as we move on. So the key insights we need here is that even if the expected value of Sn is 0, the walk can drift far from 0, even if the expected value is 0. So it's no guarantee. So the variance increases with the number of steps. Okay, then the process is random but statistically predictable. Okay, though it is random walk, but it is statistically predictable. So we have some practice problems. First of all, we have some questions about basic understanding. Define the simple random walk Sn and explain the role of xi. Okay. So xi talks about the step you take. So xi can be +1 or -1 with probability xi equals +1 is probability p, xi equals -1 is probability 1 minus p. For a symmetric random walk for question 2 now, p is simply 0.5. So probability that you go to plus xi is +1 is 0.5, and probability so so this is just this now. So probably if probability that xi is +1 is 0.5, what is probability xi is -1? It's also 0.5 because the two must add up to 1 for sure. And that gives a symmetric random walk. So computation of expectation and variance. Of course, we just use the formula. Computes the expectation of S10 when P is 0.5. Of course, when P is 0.5, we have a symmetric situation. So the expectation is simply 0. Then when compute the variance of S10 when P is 0.5. P is 0.5 talks about symmetricity. That means that the variance of S10 will just be the number of steps, which is 10. Then find the expected value of S20 when P is 0.6. Okay, so we have we want ES20 and 1P is 0.6. So we have expectation of S20. So 1P is 0.6. So we know that expectation of Sn is will be given as n into 2P minus 1. I always want to be sure. Is it 2p minus 1 or 1 minus 2p? 2p minus 1. So it's 2p minus 1, yeah? 2p minus 1. Okay, so of course, from here now, from this place, we extract that n is equal to 20, and we already have p to be 0.6. So e s 20 will just be 20 into 2p, that's 2 times 0.6 minus 1, like that. So that's 20 into 1.2 minus 1. So that is 20 into 0.2, I believe. So that is 4 in short. That's 4 for the expected value, like that. So you can always go on with that. So find the variance of S21P is 0.6. Okay, variance still the same thing, except that now the formula is different and it is not symmetric. So if it was to be symmetric, we just know that the variance would be 20. So, but now that it is not symmetric, we use the formula of variance. Variance of Sn is 4np into 1 minus p. Okay. Variance of Sn, variance of Sn is 4np into 1 minus p. 1 minus p here. So we then have 4. Okay, now variance of S20, variance of S20 is 4 times 20 times 0.6 into 1 minus 0.6. So that is 4 times 20 is 80. 80 times 0.6. That is simply 8 times 6, which is 48, multiplied by 0.4. So 48 times 4, uh, that should be like 19.2, I believe, because 48 times 2 is 96. 96 times 2 is 192. Okay, so that's to one decimal place. That's 19.2 being the variance. Okay, so for P is 0.3 and N is 15, compute expectation of Sn. Of course, that will be 15 times 2 times 0.3 minus 1. So that goes. So I think this is going to be negative now because 2 times 0.3 is 0.6. 0.6 minus 1 is minus 0.4. 15 times minus 0.4, that'll be minus 6, I believe. Then probability calculation. When what is P? S2 equals 0 for a symmetric random walk. Of course, this one now, you go one step forward, one step back to go come back to 0, like this. What is P S3 equals 1 for a symmetric random walk? So for S3 now, to get back to 1, so you take one step, step 1, step 2. So it means to take 2 steps forward and 1 step backwards, and then you have all that. Okay, so you want to follow the example that was given before to do all of this. Yeah. So then we have combinatorial reasoning. How many ways can a walk of length 5 end at position plus 1? So that's like 5 combination. Okay, depending on the number of steps you have to take. So you take to end at 5 steps, right? So it means you have to take 3 steps forward and 2 steps backward to end at position plus 1. So how many ways can a walk of length 6 return to 0 and all that? So try out all of these things and let's see how helpful, how well you understand the whole idea. Let me know how helpful this is, and if there's something else you'd like me to try out, feel free to let me know. If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, why not go ahead and do that right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, um you can also become a member of the channel by clicking on join, and that gives you some special privileges that you find when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.